Welcome to the last lecture in Chapter 2. This is 2.8, Linear Approximations and Differentials. So, what are linear approximations? We know that the derivative of a function is equal to the slope of the tangent line at a given point. And the curve of the function lies very close to this tangent line, especially the closer we are to the point of tangency. Right? We can even see that here, that the closer we get to the point, the closer the two graphs are becoming to each other where they actually intersect at the tangent point. If we zoom in toward the tangent point, if we made this graph larger and larger and we're closing in on the tangent point, then actually the graph of the curve, the yellow graph, would also look like a straight line the closer we got to it. And you can think of this like the Earth, right? The closer you get to the Earth, like standing on the Earth, we cannot notice the curvature of the Earth. Even when we're looking at the ocean and looking far out to sea, we still can't see the curvature of the ocean, okay? Or the curvature of the Earth, not the curvature of the ocean. So the idea here is that if we can figure out our derivative and our linear, if we can figure out our derivative and then the equation of the tangent line, since the tangent line equation is a simple linear equation, which are often easier to solve than curves, that we might use our equation of the tangent line to estimate some other values along the yellow curve here, but close to the point of tangency, to get pretty close approximations and to make the calculation simpler. So the linear approximation is the idea that if we use a linear equation, in this case the equation of the tangent line, we can probably find within some reasonable error accuracy values for the function close to that point. Okay? Again, because often a curve has some pretty yucky, excuse the term, exponentials or polynomials in it. All right. So again, linear approximation is the idea that using the tangent line equation is an easier calculation to find original function values. Those are in yellow. And it's really it's easier to find approximations of original function values, at least nearby values of x, nearby the point of tangency. In other words, we use the tangent line at the point a, f of a, or, again, this a is the, there we go. A is the x value, and f of a would be the y value at this point, as an approximation of the values of the curve for, again, values close to here. I feel like I've said that 6 times now. So remember, by our equation of the tangent line, this just says that y equals f of a, which is the y value at a, plus the slope times x minus a. Now remember, this is just the point slope formula. y2 minus y1 equals the slope times x minus x1. And in this case, we're given the value a as the original x value. So the original function approximation is actually this equation. We just put an approximate in here because now we're using the equation of the tangent line and not the original equation. So this is the approximation. This is the linear approximation of any curve. And it equals, again, just what we saw with the equation of the line for a tangent. It's the y value plus the slope times x minus the difference in x values. Okay? So an equation of the tangent line, we've just seen this. I don't know why I keep overlapping. So there's our original. This is no different than finding the equation of the tangent line. Okay? So find the linear approximation of f of x equals x squared at x equals 3. Well, this is a simple calculation. We could figure out what this value is when x is 3. Y would equal 3 squared, or 9. So now let's look at our approximation using the linear approximation. Okay, so the first thing we need to do is find the derivative, or the slope of the tangent. Well, the derivative of x squared is 2x, and if we want the derivative specifically at x equals 3, we plug that in, and we get 6. Okay? Remember when we can find the equation of a line two ways. One is we can plug this value in and find y, and then do the y minus y1 equals slope times x minus x1. Or we can simply use the y equals mx plus b, which is the slope-intercept form. Okay? We still need the other value of y, and you can do either of these. So I get y, which is 9, equals the slope, which we said was 6, times the x value, which was given in the problem as 3, plus b. Okay? So I get y equals 9, which we calculated here. Y equals 9 when x equals 3, and we figured out the slope, which was 6 up here. And then from this we can calculate b, which is negative 9, which then gives us our equation of the tangent line, y equals 6x minus 9. Okay? So our linear approximation is exactly the same equation, a little bit different notation. F of x is approximately equal to 6x minus 9. Okay? Now we actually found the derivative exactly at that point, so it should be a pretty close approximation. So notice if we plug in 3 here, we already said that when x is 3, y should equal 9. If we plug in 3 here, we get 6 times 3, which is 18, minus 9, which is 9. So our approximation is right on target here in this example. All right. So again, I'm just giving you some of these. Oh, did I do that twice? It looks like I've... So the equation of the tangent line we've seen, we're now using that with new notation, which is you see in yellow here, to do the linear approximation. And so from the problem we just did, the linear approximation is f of x is approximately equal to 6x minus 9. So this equation, f of x equals x squared, is approximately 6x minus 9 as long as we stay near 3. That's all that's saying. Okay? If we get too far from 3, it's not going to work anymore. Or the error is going to be higher. So this is not the equation of a tangent line. It shouldn't have an approximate there. It should say f of x equals f of a. But the equation of the tangent line is the linear approximation, which you see there. Or it might be called the tangent line approximation. Both of those are equivalent. They're just different ways of saying the same thing. Okay? We also can use the equation of the tangent line as what's called the linearization. Okay? And oops, here you can see that this is the notation here is L of x, which is the linearization. And again, it's giving you an equation near that point A that approximates the values near there using a linear approximation. So the big difference here is really notation. If we're looking for the linearization of a function, then we use L of x and we just use equal, but notice it's the same equation of the tangent line. So our linear approximations are all built on the equation of the tangent line. You might hear linear approximation. You might hear tangent line approximation. These are the same. Notice that we use the equation of a tangent line, but then we use different notation. F of x is approximately this. If we're talking about the linearization, it's actually using equals and then just different notation, a capital L of x. All right. Now, why would we want to do that? So here's a problem. Find the linearization of f of x, which equals the square root of x plus 3 at x equals 1. So here it's just asking us to find find the equation of the tangent line, and then substitute it in, knowing that the linearization is giving some approximation of the curve. All right. So first we need to find the derivative. Remember that a square root is whatever you're taking the root of, it's that raised to the power of 1/2. So when I take the derivative, I get 1/2 times x plus 3 raised to the negative 1/2. 1/2 minus 1, negative 1/2. Which means that I get, if I put this back into radical form, 1 over 2 times the square root of x plus 3. Okay? Because notice here I get the square root, it's negative, so it goes in the denominator, and there's already a 2 in the denominator. Okay? If I plug my value of 1 into this, it's quite simple. 2 times the square root of 1 plus 3. The square root of 1 plus 3 is the square root of 4. The square root of 4 is 2, so I get 1/4. All right? Now I know that I can find my x and y values here. Notice that we were given the x value, and when x equals 1, y equals 2. You can see the calculation there. So now I can plug this in and calculate my b, or I can just put it in the y minus y1 equals slope times x minus x1 and simplify. But if I do these calculations, I can see that my y-intercept is 7/4, and now I have my equation of the tangent line. The last thing I need to do is just to rewrite it in the proper notation, which is substituting in L of x equals for y equals. Okay? So again, this is replacing a curve with a straight line to approximate values close to the point of tangency. Okay. So now we want to go back and look at that, and we can see that we get the exact same thing, right? So f of 1 is 2. We already found that up here, plus the slope times x minus a being the given value. This is the other way of finding this formula, right? Using the point slope formula. And when we simplify, we get the exact same thing. Now we're going to use our example, what we finished in the last one, to approximate the numbers 3.98 and 4.05. Okay? So this is an example where, I mean, of course we have calculators now, so finding the square root of 3.98 is quite simple for us because we plug it in. But this is a way to find that value without using your calculator. Okay? So the first thing we have to do, we already know the linearization, but we need to figure out what x is in these problems. Okay? So notice when we're looking for the square root of 3.98, our function that we approximated was the square root of x plus 3. So in order to get the square root of 3.98, what would x have to equal? What would x have to equal? Well, for 3.98, x would equal 0.098, because notice inside the radical we have x plus 3 or 3.98. If we set them equal and solve, we get x equals 0.98. The same with 4.05. We get x plus 3 equals 4.05. So in that example, x would equal 1.05. And it's important to find those inputs because we're going to need them to approximate the y value. Okay? So now we simply find the linear approximations. Okay? So here, the square root of 3.98 would equal L of x, and remember we just said for 3.98, x is 0.098, so we'd put 0.098 here, which you can see, and then we plug it in for every place there's an x, and when we plug it in, we get 1.995. Now remember the actual answer, which we would expect it to be, right? Because it's the square root of 4 is 2, and this number is just slightly smaller than 2. We can do the same thing for 4.05, noticing that x is 1.05. We plug that in and we get 2.0125. Again, similar to what we'd expect. Now this is asking us if they're over or under estimates. Okay, let's look at that. Well, if we look at the curve, we can see that the tangent line is above the curve. So these are both over estimates. These are both over estimates. Okay? So how good are these approximations? Well, the closer you get to your point of tangency, the better they are. And when can or should we use them? They're often used in the terms of error rates or constraints, like maybe strength of materials, etc. We want those to be within a certain range. And so these approximations can help us figure out how to, what values are valid for keeping, for example, error rates down. Okay. So you can see such a problem here that's underlined. For what values is the linear approximation of f of x equal to square root of x plus 3 at x equals 1 accurate within 0.5? Okay, so we've already done this problem. We've already had the linearization. Once you have, if you're doing this from the beginning, you'd find your linearization, and then you'd set up this constraint equation that we want our answers to be within 0.5 accuracy, an accuracy of within 0.5 numerically. And so what we do is we set up the equation that the negative error is less than the equation, the original equation minus the approximation, right? That's the error. So if my original equation said that, you know, when they put in the value 1, they get 4, but when I put in the value of 1 in my approximation, I get 3, then my error is off by 1, right? 4 minus 3 is 1, okay? So we want this approximation, the difference in the actual versus approximation, to be less than or equal to 0.5. So I set up the equation, negative error is less than that difference is less than error, and I get something like this. So this is my linear equation. Notice now I've got the error on both sides, and I added my my approximation, and that's the original equation. I added I guess, what do? We multiply by negative 1. Boy, I did this really backwards. I should have just moved that over, but that's okay. So I multiplied by negative 1 so that these were in reverse order, and then I added the original equation to both sides so we can solve for x, okay? So we want our error to be within 0.5. So our approximation is within 0.5 of the original equation, and we could start out that way as well, okay? So we want to find the interval endpoints of P and Q in the diagram. Notice what we've done here is we have a new graph, which is x plus 3 minus 0.5, and you can see that below the graph. All we've done is taken this graph, the original graph, which is this curve, and the distance between that and this new blue curve below it is 0.5. We've just subtracted 0.5 from everything, so the whole graph is just shifted down 0.5. And we can also see here that we want the constraint above it to be the same, so this width here is 0.5. And we can see from our tangent line intersection that we don't even need to consider the x plus 3 minus 0.05 because our tangent line is above. So we only need to consider this right side of that inequality. Okay? When I do that, so all I'm doing here is I'm solving for x. I'm going to multiply by 4 and then get all my numbers on the same side. And what I eventually get is the intersection of these 2 points is negative 2.6, which is less than x, and which is greater than 8.6. So as long as my x values are between negative 2.6 and 8.6, then my approximations are within the range that I've given here. Okay. Let's see, what else do I have to tell you today? Approximations are sometimes found in the notation of derivatives. For example, if we think of the notation f prime x equals dy dx, then just by multiplying both sides of the equation by the denominator dx, I get something that looks like this. dy equals f prime x dx. Okay? Now if you look at this graph, the dx's are the difference between x's and y's from over some interval. The dy is actually the difference at that interval all the way to our linear approximation. Okay, so the delta y is the actual approximation, and the dy is our approximation. Our delta y, is the actual difference between two y values, and our dy is the difference between the original value and our tangent line approximation. Okay? So remember from our last example, we got that dy was equal to dx over 2 times the square root of x plus 3. And in our last example, we said that we were looking at a equals 1, and that dx, which is equal to approximately delta x, is equal to negative 0.05. Then if we plug that value in, dx is 0.05 and x was 1 from our problem, we get dy equals 0.125, and if we plug it back into the original kind of linear equation of it, we get the square root of 4.05 is equal to f of 1.05, which equals f of 1 plus dy, which is actually exactly what we found. Okay? I think we have one more example here, and this is another example of calculating error. The radius of a sphere was measured and found to be 21 centimeters with a possible error in measurement of at most 0.05 centimeters. What is the maximum error in using this value of the radius to compute the volume? So we're not sure our measurement of the radius was accurate, and we're trying to figure out how much error we would have in the volume, because remember, volume is a function of the radius. Okay? So again, what's the maximum error in volume given a 0.05 centimeter error in radius? Okay? Remember from our related rates that a volume is equal to a function of radius, 4 pi r cubed. And if the error in radius is denoted by dr, right, that's the problem in radius, this equals approximately 0.05. Okay? This is a given in the problem. The radius of the sphere was measured and found to be 21 centimeters with a possible error. Okay? Then dV is what's going to be the error in volume. Okay? So if I take thinking about dy equals f prime x dx, remember that's the kind of setup equation I gave you, or the definition, then we're looking at dv. Well, dv is equal to 4/3 pi r cubed, the derivative of that, times dr, right? dv dr, if I take the derivative with respect to r, I get 4 pi r squared, and then to find dv, I just move the dr to the other side by multiplying both sides. Okay? Now remember, we can plug this in to find our maximum error. So we have two variables here. We have r, and we know that the radius was found to be 21, and then we have dr, which is the error in our measurement, which is 0.05. So we plug these in, and we get a maximum error of 277 centimeters, cubic centimeters. Okay, that's our maximum error. So if we have a 0.05 centimeter error in measuring, then we have a 277 cubic centimeter error in volume. Okay, this is the same problem. It's just a little shrunk. And remember from the last one we just saw that we got a max error of 277. Well, this may seem large. A better way to understand errors is actually to calculate the relative error. Now what we calculated was the error in the function, and that gave us 277. But we also want to calculate the total functional values. That means plugging in values and calculating what, in this case, what would the total volume be. All right. So notice that the relative error is just the delta concept over the actual functional value, the delta of the volume in this case over the actual volume. We already had a formula for dV from the last problem, 4 pi r squared over dr, and our formula for volume in general for this sphere is 4/3 pi r cubed. We can reduce this, and if we reduce this, all we have left is 3 times the quantity of dr over r. Now what does this mean? It means the relative error in volume is 3 times the relative error in radius. And you can see that big 3 out there. Okay. So if I want a percentage error, I just take that rate and then multiply it times 100. So I use my maximum error, VR times R over R times 100, and I get 0.05 over 21, which these are both givens in the problem, times 100. And so I have a 24% error in radius. Okay? Or, and if I use that, then I have a 72% error, potential error